Thank you very much, Professor Lewis and Professor Norton, for organizing this exciting event. And I'm much grateful for Nanonics, in particular Professor Lewis, his pioneer work on near-field imaging probes. As a graduate student back then, I read many papers and I try to follow a lot of exciting examples. So today I'd like to share how far we have gone also in the around the road of near-field imaging probes. I will call it still a work in progress or a long say a long way to go along this line. But maybe there are something that we have learned or enjoyed by far. And so why we are interested in that? As some of you may know, I'm more of like optical nanofabrication person. We make or generate nanostructures, nanocavities, and nanoantennas, and so on. And we use near-field probes in different aspects, trying to study how light is being delivered, confined, and converted into a different form of energy that includes, for example, how this is enhancing our way of extracting light or using them towards manipulation and so on and so forth. So this is actually what really brings us to the near-field optics. But I will say that there is probably something even bigger than that. If we compare what is now achievable, for example, in the radio frequency engineering, now almost everyone has a say a Wi-Fi device in your cell phone, your computer, and so on. Right? It's a great success. On the other hand, if you think about how optical engineers has advanced, now they start to make photodetectors that are small compared to the wavelength. They're making photo emitters. They're making amplifiers, also in the deep subwavelength domains. So maybe 20, 30 years down the road, we should expect something that is like optical circuit, optical network in the small, very small deployable domain that can be used for chips, that could be used for imaging, that could be used for communication at a confined space like what we have to do for microscope. Of course, this is still a very far-fetched problem. But here is a challenge. In radio frequency, we have a very nice faithful comparison of what is, say, time domain simulation or all this, advanced microwave simulations, and this is all enabled by experimental validation using a very fine probe. By definition, all the radio frequency measurements using a metallic stylus is near-field imaging. Because we're talking about a wavelength that is close to maybe 12 centimeters or so, yet the tip size is millimeter. We really have far better spatial resolution that is achievable in this domain. And of course, when you teach college physics, you see how nicely we can inject current, we can map the space, we can generate a beautiful probes or plots on the oscilloscope. Comparing near-field imaging that we use nowadays, for example, an enzyme tip, we still have a lot of challenging issues, even after, say 20 years or more of development. I think we still have a limited success in making good aperture, good tips, and there's a good reason for that, and resolution is still limited to about 1/10 of the wavelength and so on. So this is actually representing a long-standing challenge about how to measure near field. And associated with that is really our textbook problem about antennas. If you take a cross-section of that near-field probe and consider that is an antenna, and then we see there's really a issue regarding the gain, regarding impedance match. The antenna cross-section usually is a scale of wavelengths. You want to collect a light that is, for example, submitted or confined within, say, a quarter wavelength spot. yet you have to push it into a gap. This gap or a hole can be of a diameter d. Yet the typical antenna gain scales with lambda divided by d to the power of 4. So in other words, you're really using a very lousy circuit or circuit probe in that sense to achieve a goal that requires ideally a 50 ohm circuit probe that we hope to have. So there are a lot of those challenges that we think there are still great room for improvement in designing and designing the probe and designing the circuit in general. So I won't repeat. There are a lot of studies along these directions. Many creative engineers have already experimented and tried on that. One of the famous examples was this beta bootcamp problem associated with the low throughput of a hole. If you think about a pinhole on the very end of the aperture probe, then the power that is allowed, this pinhole that is allowed is order of like Ka to the power force. In other words, if you have a pinhole that is smaller than 50 nanometer, then theoretically you only have about say less than 1% of energy transmitted through. So this is actually being challenged recently by many different works, including Professor Thomas Edison, who just got the Kavli Prize of Nano-Optics or Nanophysics. And inspired by that, we decided to use this hole as a simple example and study how transmission could be really interpreted or affected. Here is a near-field probe, but what we are trying to do is to map light transmitted through a hole. And this hole is about say 100 nanometer wide across a film of about 80 nanometer in thickness. And as I told you, if I was just treating my near field imaging probe as my spatial circuit probing technique, then I could do the mapping both in XY dimensions as well as along the Z direction. And this is a typical measurement we obtained at the wavelengths of say 633 nanometer. The center, of course, has a lot of light leaking through, but also if you look at this fringe associated on the surface, they actually indicate a horizontally polarized say dipole.
Excuse me. Yes. This is of a probe in a flat plate?
Yeah, it is a probe in a flat plate, but there is a hole on the plate.
In a flat plate. Yeah.
Right. Okay. Right. And then you take a distance away. You could you take the tip away to say a micron above or so, or you can start to map them layer by layer, and this is what we usually get. And a very interesting fact to us is that now the center of the pattern actually becomes dark rather than bright. And the radiation actually is of some kind of dark fringes by nature. So how to interpret this? We found that if you collect it in like different height, they actually the rings, all this set of concentric rings getting darker, bigger and bigger. Well, the center still remains dark. So there must be a very simple reasoning behind it, and I think we can simply just borrow the holographic model into this scenario. If we consider there is actually two components instead of one that is allowed to transmit or propagate in this second half space, then one, for example, is the plane wave. Even though the film is about 100 nanometer, there are actually significant portion of light that is allowed to tunnel through, maybe 5% or so. But the hole by itself also generated some kind of a spherical wave. Here I use a simple scalar expression, even though you could also consider the vector nature. But in combining these two, I can start to measure, for example, a phase difference between the spherical wave and the plane wave. And this is actually resulting in a very nice fit. If you do this type of fitting, you can start to measure both the amplitude and the phase as a result of this holographic imaging. And here we can, for example, tell precisely the phase lag experienced by this tunnel or scattered light when the tunnel is tunneling through the hole. I think I just repeated this. Let me just yeah. So this is just unfortunately a repeated slide. Here is what we actually obtain in such an experiment, in such a near field experiment. For a hole size that is close to about 100 or 60 to 160 nanometer, we found that the obtained amplitude that the light scatters from the hole actually is by a factor of say 2 at least larger than what beta theory actually suggests. In the case of the smaller hole, this deviation is even stronger. So in other words, we actually cannot treat the thin film of metal as just a lossy conductor, but we have to incorporate, for example, the so-called geometric inductance into the picture. And the other important part is that the beta theory actually was originally assuming some kind of conducting, very conducting string, but all metals, as you may know, in the optical frequency are strong deviation from such a conductor or pure conductor picture. And this is also validated by looking at, for example, the effect of a phase difference across, say, different film thickness. We can measure such a phase dependence as you increase the film while keeping the hole small. Yet the energy decay actually seems to follow very nicely. So the film actually is doing what they are supposed to, block the plane wave, yet leave behind a very interesting retardation for all those features that are generated. Here is another nice example that really made me inspired. If we have different say, surface features, on the left is a small dent, on the right a disc that is or protrusion that is being placed on this surface sample. Then what we see is that there is actually an inverse phase shift. For the dent there is almost 180 degrees phase flip compared with what is left out as a protrusion. This is somewhat similar to now the well-known what they call the Babinet's principles. Right? You really could also identify that by considering the polarizability of such a cavity versus the metal disc antenna incumbent. So this is quite nice with all what Ensemble can offer. And of course, and then you start to change the illumination. You start also you can observe the effect of say phase gradient in the illumination direction as a result of now pattern or forward emission across those whole arrays. So all of those actually suggest that we should have considered not only just a magnetic dipole as what Beta's original theory suggested in the hole, but also a vertical electrical dipole in the system. So that's a very simple element, but I think now we can really use this near field imaging technique to extract not only just the intensity, but also some of those retardation effect, if you want, and study and use this towards a more collective behavior. As an example, I'm just going to show you that if you have changed this thin film of gold metal to a more structured film, in this case you can think about those as like antenna arrays, but we purposely build a center hole, so this very center is actually a through hole. This actually allows us to study now a structure that, if working properly as a collective effect, give rise to a so-called near zero index of refraction. In other words, if you excite the system originally with some kind of say distributed phase, after the system after light emits out of the system, the phase becomes more uniform, more homogeneous. And indeed, this is confirmed in the numerical simulations, where if you shine light of 1.5 micron in such a structural layer, the outcome, say, light field or wavefront become more homogeneous. And experimentally, this is what we have seen. Once the light is polarized, properly along this thin wire direction, aside from this very bright spot that really indicate a through hole, there is a broad area about 7 micron across that all have shared almost similar phase front. So that's actually quite encouraging in terms of near field imaging. Although I have to admit, all of those experiments, as I said, is really gathered point by point and takes a long time and a lot of patience to accomplish. So with that, I'd like to tell you a different story about the nano antennas. I was already telling you how we can use this ensemble and to look at the phase contribution of the nanostructures. But there is another important aspect that we hope to take such an image, near field image, in the say high resolution and real time. In fact, this electron beam imaging is a very nice and convenient choice, provided in the literature, maybe back in the 70s. Some of the papers in the 70s were using that to measure electron-photon interaction. And there's a clear advantage. And if you look at the surface, say, excitation like surface plasma, they naturally requires a very large momentum. And such a large momentum can be provided by considering the incident momentum of the electrons. And not surprisingly, actually, back in the 70s, people are already using the oscilloscope in that sense. By injecting electrons, they can start to measure the energy loss of the scattered secondary electron and plot them, for example, on at that time, again, a fluorescent analog oscilloscope. So we have heard a very nice talk by Professor Nagel on what is CLs doing in the, say, bulk material. But I like to just simplify the picture so that a entry, say, a graduate student can make use of such a system nicely. So there is a injecting current, and this injecting current, if we really control the electron beam very properly, has a spatial spread less than a few nanometers. This is what really electron beam optics really can offer us. So I can treat this as an oscillating dipole or some kind of time-dependent current. And this is this current is doing work so that it radiates out, or it is converted to electromagnetic field. then there are two components, radiative component and the scattering component in the system. And in terms of the total measurements, we are actually measuring the rate of photon released to the system in the cathodoluminescence case. So that's the radiative lifetime that we are measuring. Whereas if you are more concerned about the so-called electron energy loss spectroscopy, looking at how much energy is reduced after the scattered from the samples, then this is the total energy loss or energy transfer rate that is being met. So just putting those two aspects into one example, if we have say nanodisk and we are trying to do this measurement in both cathodoluminescence, or electron-induced light radiation, and that of the total energy loss experienced in the system. This is what we typically obtain, and all those blue curves indicate that we are really harvesting photons, and if we do it properly, we can really map this energy and location in a proper way. So here is just a simple example that we were doing in the scanning electron microscope. If you have a sample here, for example, if you have a gold bow-tie nano antenna, and you're injecting electrons into such a system, and you can allow the electron to scan over, say, confined space. For example, you can think about this is almost like you're doing a radio frequency antenna measurement by injecting a current or current flow from the very side of the antenna, and you're looking at how this antenna is radiating out. This is what we can measure. Just simply, you convert all those systems to an optical frequency. This is what you can measure by harvesting outgoing photons through the parabolic mirror.
This is in a SEM or in a?
In a SEM, yeah. So electron is coming from the top. It bombards the sample. It generates, say, secondary electrons and secondary photons or particles. However, what we see is really just the result of photon generation rate as you move electrons across different locations. Right? So we are scanning electron as the way we are doing the regular SEM image, but what we are plotting is a photon map. It's a photon generation map, or the number of photons you can collect as this injection source is moving around this.
Is the CL image panchromatic?
It is a panchromatic image. I will show you more of those, monochromatic or filtered images. So it actually offers a pretty high spatial resolution. Despite that, there is all this electron spreading effect and so on. Here we really can see high spatial resolution. Here, the depth of this photon antenna is less than 30 nanometers. You can really resolve them very, very faithfully. And it is done all in real time. So
I wonder in the center image on the right, there's a dark, the dark spot in the middle.
Yes.
That's when the electrons go right.
Right at the very end. Yeah. So at this dark spot is this black spot is where we can harvest the photons from a gap filling condition. So all this part is very simple. It's all like far field spectrometer and optical measurement technique. But yet the possibility of injecting current in such a vertical fashion and localized fashion really offers some new opinions. So again, I was trying to tell you that I want to make things simple. It's not that you cannot do better modeling or theoretical interpretation of that. But let me just assume that the most important impact is when the electron is hitting the surface and converting to, for example, electron hole pairs or so on that is causing radiation, right? So this actually has a lot of history in the background. For example, fluorescence, metal-enhanced fluorescence emission is a famous example. Ford and Weber back in the 80s studied this problem, and I wanted to take a closer look at that because if we again come back to the amount of work done by this radiating dipole vertically, pointing on the surface, there are actually different components that we can analyze this. Because I'm an imaging person, I was trying to tell you. So you can actually decompose now those different components by their lateral momentum. Some of them, if there is a small lateral momentum or a wave vector, then they radiate out directly through the free space. But there are also a significant portion of that is coupled to the surface mode. Those surface modes have a relatively larger lateral momentum, and in other words, they are spatially confined. So, and if we compare the amount of power that is being converted from the dipole to the electromagnetic field, we see there is actually a very narrow spike that is centered around the surface mode excitation. This comes back to the spatial resolution. If we are really just concerned about photon traveling on the surface, here I have a really a good rationale to tell that the mapping can be local, can be of a small resolution. And indeed, this is being kind of studied and compared in different modes. We have seen those papers, for example, about single nanoparticles. Here, I'm again using a triangular particle, nanoparticle on say a silicon substrate to validate our comparison. So here we are actually doing a modeling using injection current approximation. Again, I assume that the current is gone after I have injected into this location. Here is what we obtained using finite and different time domain simulation. So, we don't have any good agreement in the long wavelength regime, but in the case of surface mode excitation, where plasma is really the prominent factor, we do see a good agreement. And if you would like to read more details, there is a paper that we published back in 2009. And here is another example. This is again a measurement on a nano triangle, and if I can do this simplified form, the scale of this triangle is about 300 nanometer, and we could now do some kind of monochromatic imaging experiment, and this is actually quite new. I would say half cooked yet. Some at a wavelength of 625 nanometer. Again, if we neglect all the secondary electrons, contributions from secondary electrons, this is like an eigen mode of the triangle, and this is what the energy transfer rate should look like. And I see there are good comparisons, even though I cannot say that we have all details nailed down. So I wanted to say that radio engineering or antenna engineering really offers some good insight for those type of experiments. To do better serial imaging, we found that it is really important to lift the antennas or to make the antennas high enough above some kind of say high index background. So we already know there are waveguiding effects through those. And those waveguiding effects actually take away photons. We are only placing a detector at the top half surface or half space. So the more you can lift it up, the more we actually are allowed to harvest photons from, for example, the free space side. So this is actually indeed confirmed with some of our lifted antennas using fabrication method. Here again is another like array of cavities. Those cavities are actually quite unique that they are of only the light are mostly confined within this 2 nanometer germanium layer, where the top is capped by a silver layer. What we have done is changing the thickness of the silver layer and change the actual size of those silver structures. So panchromatic image, everything looks very similar, but once you start to do the bandpass images, you can really tell now the fine difference enabled by this plasmoluminescence technique. And I have to say that this is also a quite unique in terms of e-beam lithography or e-beam imaging, because it allows you to penetrate through the top metal and access some of the information that is embedded in the ground. I think there are a lot of great examples from gallium nitride or other say light emitting devices. Here we see that metal is no exception. And if we do that by properly protecting, for example, the contribution of this excitation source. Here again, I'm just assuming a simple vertical excitation, vertical dipole excitation. Then I can start to map it into like a array of discrete elements in the antenna. And long story short, if I can really do this, by injecting electrons through the gap, what we typically consider as a dark imaging mode or dark mode is actually an efficient radiator. They actually radiate quite effectively, except that they are only radiating to the side band, to the angles that are larger than 45 degrees or so. And compared to what you really see in a typical like dark field microscope, where this bright mode is only allowed by their symmetry. We actually can have a significant gain in photon. And this is what really compares with this light decomposition theory or image mapping by looking at how different injection of this small current source really could help us to understand the imaging in such a nano antenna system. So I'm probably a little behind. How much time I still have? Maybe I should just say there are great examples that we can study using this. This is still an ongoing effort, but hybrid solar cells is one of the examples, and why we are concerned about it. There is really a mismatch between the need to absorb photons, in which all those hybrid organic solar cells are poor absorbers. But on the other hand, we also want them to transport electrons very efficiently. So we have to keep collecting wires and devices in the proximity. By incorporating say nanoparticles, metal nanoparticles as antennas into the system, we do see some hope. The improvement is mostly around the band edge of those hybrid organic semiconductors. In our case, the improvement can be as much as like 70 or 80% for the 700 nanometer wavelengths. We heard a nice example or idea about photon recycling. I think photon recycling really does well for the organic solar cells, because here we are really boosting the radiation rate. The system actually has a poor absorption or light management to begin with. If you add nanoparticles, even though there are some loss involved in this non-radiated component, but overall we're actually boosting the photon conversion by just forcing them to go in and out multiple times or more frequently. So that is something that we recently found and in good agreement with some preliminary experiments done using those particle-loaded solar cells. So with that, I hope I give you some examples of how can we use near-field imaging creatively, both in the extraction of phase as well as the injecting current into study antennas. In terms of how to design those type of surface or antennas, I think there are many questions, and this is really just the very beginning, and of the whole exciting roadshow. And thank you very much.
Are there questions?
Could you comment on explain more the dark versus bright mode structure? You showed this triangular silver localized surface plasma resonance, which I would think wouldn't couple very well with dipole radiation, but somehow it's still bright in your measurements. I didn't understand.
Sure. That's a great question. So, yeah. So how is this done? This is done by injecting a vertical current to the horizontal pair of the triangle, right? And in order for this system to respond to this dark mode, you actually have to think about the antenna by itself. This type of antennas are not that subwavelent. So there is actually a phase retardation. So in this case, for example, at the 45-degree angle, you can consider there's probably like more pronounced effect from one side of the antenna than the other that contributes to radiation. This is actually the thing. Yes.
Quite a different question. You mentioned in the passing, sequential measurements take a lot of time.
Yes.
So I'm sure you must have speculated or thought about how you can parallelize. Is there some way you thought of parallelize your measurements?
That's a great problem. I think if we try to parallelize those measurements, we probably have to go by more structural illumination, more of those dynamic form of injection and collection. Those are probably the opportunities along the lines. Yeah. If once we have all this mechanical movement of a collecting probe, I think our limitation is really how fast we can move those mechanical probes. But if everything else is not mechanically driven, we can do it in parallel.
So in circular relation, you would sequentially have 3 or 4 different patterns, or
yeah. So you could start to vary the patterns. My group will also play with a lot of those digital light manipulator or modulators. Yeah, you can do that by basically changing the illumination of phase.
The challenge, which is, there's a paper now from the group in Berkeley, which I think tries to approach that challenge. Okay? But the real challenge is how do you take these type of concepts, and on flat surfaces they work very well. Okay? But if you want to put it at the tip of a probe that has AFM capability and has high throughput, okay, it is a complicated challenge. Even the Berkeley work, I would say, has not achieved the challenge because the probe is very large. Okay, so the bottom line is that this has been the real challenge that has not yet been met.
Right. So I agree with you, but on the other hand, I do have a more optimistic, or say, I look for if I can, future breakthroughs, right? For example, if I could think about, some of those, say, particle detectors developed in the past. Those are very expensive, very low throughput devices, but they now made it in a micro-channel platform, they can do this in a economical way, and some of them actually incorporate good amplifier, preamplifiers into the system too. So maybe in the future, semiconductor will catch up again to solve the problem of, for example, incorporating device element, not only just the tip itself, but circuits surrounding the tips that can actually solve this issue. That's just my speculation. I know it's a long way to go.
No, it's a challenge. It doesn't mean. I think these type of experiments really lead you to solving the challenge, but it's still a challenge.
Sure. Yeah.
Any other questions? If not, we should thank the speaker again. And now.